All right. Good afternoon, everyone. Happy Thursday. Happy summer. Hope everything's going well. Appreciate that you guys are sharing a little bit of time with us today. We've got a really good topic in our webinar today. We're lucky to have Jerry Rather with us, who is a longtime veteran with PTC and really knows Creo, the whole Creo suite inside and out. And he's going to talk a little bit about generative design today in a bit of a different respect, not just what it does in using AI to help create designs and products that kind of go beyond sometimes logic and thinking. It's pretty radical. I think radical is a good word for the designs and products that the AI within generative design can come up with, outside of sometimes even human comprehension. But also how to attain getting that actual from the design to the actual part, because these things are such a lot of cases, these designs are different, so different from the norm. How do you actually manufacture it? And if you think about some of the sustainability initiatives a company may have to reduce the weight of their parts, or if they just want to use less materials and have a stronger part, no matter what the purpose is, this webinar will talk about supporting these engineering workflows to help you get from that design into manufacturing. So if you have any questions, feel free to type those into the chat box while we're going, and we'll try to answer them as we go, but we'll definitely answer them at the end. We're looking at about 30 minutes today for our webinar, and without further ado, I'm going to hand everything over to Jerry Rather.
Awesome. Thanks,
Jerry.
Rob. Thank you, Rob. And thanks, everyone, for joining. So again, we're going to talk about generative design, but more importantly, what do we do with it, right? Because as soon as companies start to realize what the solution does, the immediate question following is, what do we do with this? Does that mean we have to 3D print everything we're making and generating in generative? And the answer is really dependent upon what your goals are, right? Do you need a prototype tomorrow? Is it short run production? Are you going to do high volume production? All of that kind of factors into how are you going to use that design that you just generated. So first thing we'll do is just a little bit of basically a description about our generative design solution. So generative topology optimization. The company was Frustum. PTC bought the company in, I think it was December of 2019. So we took Frustum, and Brian Thompson, who runs all of the CAD solutions and development, he basically looked at it and said, listen, we're not releasing this until it's 100% integrated inside of Creo. So the great thing is we were also doing multi-body design. So we use a lot of multi-body construction for the setup. So it works really, really nicely. So what is generative? It's another Creo solution that basically uses AI to automatically generate the optimal solution, solving for that defined set of criteria. And that's everything from your loads, your constraints, your material, and your manufacturing specifications. So rather than design a part from scratch, you're going to give it a volume, you're going to give it some preserve areas, maybe some keep out areas, and it's going to generate that design for you. So very rapidly, you can come up with a design that's optimized based on those defined criteria. We also have GDX. So generative design extension is an add-on. The prerequisite is to have GTO, but the reason to get GDX is you're going to generate a very large number of these design studies. Whereas when I'm using generative design, I'm solving locally. So I'm using my own computing power on my laptop or whatever machine I'm on. When we go to GDX, what we do is we upload that setup to the cloud, and now we're using high-powered computing to simultaneously solve for, could be hundreds of different scenarios. So the great thing is we can solve for a very large number of possibilities. But the nice thing about GDX is, think about it. If we have 100 different designs, that doesn't help me, right? What helps me is to pick the best one out of that 100. So we have a lot of really good graphing capabilities, right? And they're all dynamic and interactive. I can go ahead and start to prioritize. Maybe the priority is, minimum stress. Maybe it's minimum mass. Maybe it's factor of safety. So as I begin to play with these different variables, it's going to start to filter and give me the solutions that meet those criteria. Then when I get down to the top three, I can do a side-by-side comparison that really I can go a little bit deeper and look at each one of them. So again, this is solving in the cloud. But the great thing is not only can I solve for a whole bunch really quickly, but I can actually find the best solution based on the criteria that I specify. Another way of saying that, I mean, here's where we have GTO and GDX. Here I have my design criteria. If I'm using GTO, I'm going to solve for one defined design criteria. So I've got a material and I've got some additional specifications or constraints, right? I've got a limit volume. I defined a parting line and symmetry. I can have multiple studies. I can have multiple load cases. So when I'm using GDX, I can solve for as many of these studies as I want. And rather than just solve for this titanium alloy, I could have maybe 10 different materials. So maybe I want to investigate using different materials for whatever properties. It could be at this point in time, I can get one material cheaper. So maybe I need to look at a design in that material and what would it look like, because I could source it more economically, or even if I'm looking at the CO2 foot or the carbon footprint, where do I need to ship it from? Maybe I'm looking at recyclability of that particular material. All of those things could factor in, but again, I can solve for many and then I can choose the best one. So GTO, I'm solving locally, one at a time. GDX, I'm solving for as many as I want in the cloud and very rapidly. So why do we need it as an engineer? The goal is, hey, I'd love to design right the first time, every time, right? But I'm doing the best I can using the tools I have. When I'm using generative, I know that the design I'm creating is actually optimized to meet those criteria. So it's going to allow me to do that very quickly. And again, like Rob said, the designs that you create from generative, they don't look like I created them or another engineer, because we kind of create prismatic type of things, right? Every CAD solution, what do? We create a sketch and we extrude it, right? And would I design like this? Not necessarily, right? So it gives us a different way to think about designing our products. So that's how we introduce a lot of innovation. A lot of companies, I worked at Ford before PTC. All we did is we took the last production part and we tweaked it for the next product, right? So did we introduce any innovation? Did we improve quality? Did we improve performance? No, because 98% of that part was the same thing we've been using. All we did is modify it. So that's not going to help us to innovate. It's not going to help us to improve a whole lot. We're just simply reusing what we've already done. What we want to do is really create the optimal design. So rather than just creating a design that works, maybe we focus on creating the best design possible. So as a company, now we can look at competitive differentiation, because we're going to deliver better products, better quality products, optimized product, higher performing products, all those things. We can look at, maybe our fabrication and how we're going to manufacture it. Do we want to look at cost reduction and profitability? Rather than create this using traditional means, maybe I'm going to use generative design to tell me how I can create the lightest part possible that exceeds those strength characteristics that I need. So using generative, I can go ahead and pursue those design goals based on the criteria. Obviously, if we create a better quality part, and what we're using with generative is basically FEA, right? So we have the loads, we have the constraints, we have the materials. When it begins to solve for that design study, it knows where there's stress. If there's stress, I need material. In areas of no stress, I don't need material. So now I can start to pursue anything where maybe structural integrity is important and weight reduction is critical. So a lot of different things we can do, but if we create a design that's optimized, we know it's designed to support the loads and the constraints, maybe we're not going to have products that fail, so we're going to reduce aftermarket cost, right? It could be anything from service, warranty, any kind of liabilities if somebody gets hurt using the product, right? So a lot of different reasons to use it, but it's a different way of thinking. So when we use generative, again, the question is, what are we going to do with this thing? And this is where everybody says, hey, do I have to 3D print everything? And it could be the use case, right? Maybe I'm using it for R&D. I need this bracket tomorrow. So maybe I'm going to take the faceted results and simply go to 3D print, right? Maybe it's a short run production. I'm going to take maybe the essence of what I got from generative, but I'm going to spend a little bit of time and effort and create a cleaner version, because the reality is, I think what comes out of generative is really, it's definitely something that I would make, but there's a lot of, here I got a flat, I got a little pocket, I got lumps, I have bumps. I wouldn't go to market with that. So even if I take freestyle, I do a little bit of work, I can basically take what I got from generative, apply that, and come up with a model that I'm more happy with. And again, now I have something that this would be tough to maybe manufacture. But again, if it's low short run production, they're going to pay a premium anyway, but I feel happier going to market with this one here. Now, if it's high volume, again, what do I want to do? I'm going to recreate it. Am I going to cast it? Do I want to machine it? So here's where I'm going to put maybe a little more effort. Maybe I'm going to recreate or reverse engineer that using Creo. Now I've got a parametric model where I can really use those variables to do some optimizations and use our simulation tools to make more improvements or refinements to the model. So again, a lot of different options, but really the majority of them come down to, what do you need? Is it a prototype tomorrow? Is it short run production? Is it high volume? And how do you plan to manufacture it? Do I need a model that I can cast? Do I need a model that I want to machine in maybe 3-axis or 5? There's various approaches to do this. So it looks kind of like this. And really, where most people end up going with generative is really this scenario. They use generative as more of a conceptual design tool to say, maybe I'm going to use generative to tell me how I could or maybe should create the part differently. Then I'm going to look at, what do I want to do with it? Again, if I need a prototype, I'm good to go. If it's about high volume production, I'm going to do some other things, right? Because I'm not directly using it, I probably want to do some analysis as I'm doing the refinement and the optimizations. So using our live simulation tools, the ANSYS simulation, the Creo Simulate products, whatever tool you want to use, ANSYS simulation tools, live simulation, better for the engineer, because as I'm making changes, I can see whether or not that change is helping or hurting me, right? Versus me designing and then throwing it over the wall to the analysis group, waiting for several weeks, and they can come back and tell me it's not strong enough or whatever. And then we're going to have all those design cycles. Using live simulation, I can give those guys a model that's already proven to a pretty good extent. And then, of course, what do we want to do in terms of manufacturing? Another use case, which is really interesting, application of generative, is the whole idea of Kaizen, right? So this is continuous improvement, change for the better. So in this example, we can take generative and say, here's an existing part, right? What if I took that part, ran my analysis? I probably have some data in terms of how it's performing in the field, right? But I can do a baseline analysis, see where I'm at. Then I'm going to use generative. And instead of using a starting volume, I'm going to use the part as the actual starting volume. And we can play with the actual limits of the material. So by just backing off the usage of that available volume, I'm able to very quickly see in this design what's most important. And within minutes, I know these little structural supports, the outer support, it's really not that important. If I focus on the main beam, I'm going to create a better quality part. So even when we look at, again, taking an existing part and then using generative to quickly understand what's critical, is a really good use case for generative design. And again, kind of looks like this. I just back off the limit volume and say, if this is my available starting geometry, try to use only 85%. And as I back it off very quickly, we see what's most important. And then I'm going to go back and maybe focus on the main beams and get rid of this. So now I've got a part that's ideally stronger and even lighter than the prior version. So the reason for generative at a high level business value, hey, I'm going to get to market faster. I'm going to introduce new products much quicker. Why? Because I'm using generative to go from basically a volume or a starting volume to give me a design that is optimized based on those criteria. Now I can take this as a starting point and figure out what I want to do with it. So we're going to really speed time to market. Accelerate new product introduction, reduce product development cost. Any new product, again, a lot of these design cycles, I design, we analyze, we go back and forth using generative. I know this solution is already optimized. I'm going to put a little bit of time and effort to maybe reverse engineer this for manufacturing, but I know I got a product that is actually going to work, and I'm going to eliminate all those back and forth design cycles. In the process, I create a product that is higher quality, better performing. If I want to increase market share, sales, and revenue, looking at something like this, it's obvious this company is doing something different, right? Gain early design confidence. Again, it's created a part automatically that is optimized based on the criteria. So if that's the case, my risk mitigation, I would feel pretty good, right? Now I have a product, I know that works. So all the service, warranty, repair, liability costs, I can hopefully reduce, potentially eliminate. The other thing is over-engineered products. What do we typically do? We take last year's model or whatever it is we're working on. Maybe the loads have changed slightly. So what do? We just simply make it bigger. So bigger is not always better, right? Rather than over-engineering everything, let's focus on maybe material reduction. So how do I get the lightest part, but yet the best part for the scenario that it needs to meet? And then sustainability goals. Again, it could be material. If I can design a part with a different material, maybe I can source that material more cheaper. Maybe I'm not getting it from overseas. So think of the carbon footprint. Even taking that design, and Volvo's doing this, right? They're taking parts and they want to, I think their goal is to reduce the weight of the truck by 50%. So using generative, they're looking at all of these different parts in the Volvo truck and saying, how can we reduce the weight, increase the performance, reduce the fuel consumption? So a lot of different reasons to use generative, but really it's pretty amazing to start with a volume and give me a part that's optimized. And if I take a look at that and think about conceptual design, now it's telling me how I should or maybe could design a better part. So with that, let's jump right into a demo. So what I've got here is just some simple geometry. Again, the nice thing with generative is we use our multi-bodies, right? And this really helps me in the setup of the generative. So to get into generative, we simply go to applications and we're over here. Like every Creo application, if I work left to right, it's generally a good workflow. Here it's telling me I haven't defined the geometry. We've got no loads. So I pretty much know what it needs. So real quickly, here's my starting geometry. Where's my preserve? I want to keep this area and that. So the preserve is typically areas of your model where I want to clamp it or hold it. And so I need material. So that's what I'm saying. I don't care what happens in the available space, but I need material here. Exclude, I don't need to use or specify exclude. I could put it in the actual starting geometry. I could leave that out. These are just areas that you don't want to have the part created in because it's maybe going to interfere with something else. But again, you don't always need to define the extrude or exclude if you want to put that in your starting geometry. So once we're done with that, we got to have some constraints. So let's go ahead and do that. We want to actually have a fixed constraint here. So we're going to just specify or select that geometry. So that's fixed. right? We want to add some loads, right? We don't have anything defined yet. So we're going to put a force on the bottom there, directional force in the Y at 3,500 newtons. So that quick, we have one structural load case. The cool thing is we can have multiple load cases defined. So when we solve in generative, what it does is it doesn't combine the different structural load cases when it solves, but it creates geometry that satisfies all of them. So let's just go in and maybe modify that. I've got that force. Let's redefine it. It's going to be actually on that surface instead. And it's going to be slightly different. So let's put a $5,000 or $5,000, 5,000 Newton load right there. And we're going to do another one over here, right there. So again, directional in the X, 5,000. So that quick, we really defined it. Again, we got multiple load cases. Now we go into our design criteria. Here's where we start to specify what do we want to do. So maybe I'm going to say, I only want to potentially use 35% of that available volume. Maybe I want something that I can machine 3-axis. So let's specify a plane for that, right? Say, okay, that quick, I'm going to say, go ahead and solve for that geometry. So what it's doing is, again, using analysis in the background where it sees there's stress, it needs material. So that quickly, it's going to show me a possible solution that meets the defined criteria, right? And again, we didn't have to go back and forth between design and analysis as we were doing this. So there's one possible solution. And again, I could replicate this. I could do any number of things. Maybe we look at it and say, I want something a little more organic. So let's delete that constraint. And again, we could have multiple criteria and multiple studies. But let's just do this for now and say, okay, now let's look at something that's maybe a little bit more organic in shape. Right, so that quickly, again, it's looking at it. If there's no stress, I don't need material. So what's most important to satisfy the loads and the constraints? So here I have my model. So the focus for today is really this, because this is where people say, eh, I get it. So now you're going to show me how to go from basically nothing to an optimized model. But now what do I do? So there's different options. If we go up here to generate design, we can output the tessellated information here. We can do an auto reconstruct that takes our freestyle surface and it maps it to the geometry. It's cooler than it sounds, right? The reality is you're left with something that, again, do I want a flat? Do I want these pockets? Do I want the lumps and bumps? And really, I don't. So what I'd like to do and what most companies are doing, unless it's the need for a prototype tomorrow, they're taking this and saying, hey, now I got enough information. Let's use this more or less as a template to create the model. So let's assume we did that. And now let's show you how that's done. So let's close this and we've got a model here. Maybe we want to 3D print that. So the first thing we want to do, I need a prototype tomorrow. There's a faceted output, right? And maybe if we have an in-house 3D printer, I want to do a little bit of prep work on this model to 3D print. So the first thing we'd want to typically do is define the build direction. So whenever we print in metal, we need to have a structure to basically support it as it's being printed. So what this tool allows me to do is I can specify what's most important. Maybe it's reduce shadow area, maybe it's support volume. So I can define all these things and I can go ahead and run it and it's going to show me what the build is and actually create that as a feature. So I'm not going to do it live because it does take several minutes, but I'll show you the results here. So here I have the build direction, right? Now that we have that, I'm good to 3D print. So here we go over here to print. We go into prepare for 3D printing. There's my part. I'm going to arrange it on the tray using the build direction. So that quickly, then we can take it and I'm going to say, hey, I want to do, I don't know, 3 of these, right? So let's position them here, maybe space them at 120. And we've got 3, right? So there's a model. Now we want to generate those supports. So using our 3D prep, we partner with iMaterialize. They're like the de facto standard when it comes to these support structures. There's a lot of properties you can go ahead and configure, but they're already defined. So we directly use them inside of Creo. So that quickly, it looks at the model, it looks at your build direction, and it's going to create all the required supports to be printing. Now, if you're using an outsourced 3D printer, they don't want this. They're most likely going to create their own supports. They're going to use their own IP and knowledge of 3D printing to do it. But if you have an in-house 3D printer and you need a prototype, kind of the way you can get there using this capability. So again, there's one option. Maybe I want to take this. I've got a short run production, but again, I don't want to use that faceted model because I like a lot of it, but I don't like all of it. So maybe I want to do a little bit of cleanup. So basically what we do is we bring in that facet data, right? And that's right here. If we look at our bodies, there's that generative hybrid. So I just changed to transparency. Now we can go in and use our freestyle tool. And this is just a really easy way to create very high quality surfaces really quickly. Instead of creating curves and whatever, I'm manipulating a primitive shape. So I can take any entity, simply grab it. I can grab an edge, a face, a vertex, and we can begin to make some quick changes to it. So if we look over here, maybe we see that we're off. Let's take and grab this, hold down the shift key and take these. If we maybe set that planar, let's turn on our datum planes and set it planar to there. Now I've got something we can go ahead and match and do whatever, right? So really quick, really easy to use, different modes of working. I generally switch between the two. If you go to the box mode, to me, a lot of times this can be much clearer when I'm working, depending upon how complex it is. So what I'm going to do here is simply join those two. And if we take a look, it's done all that and it creates very nice geometry, right? If you put this in analysis, you look at porcupine, whatever, it's very smooth and very good looking geometry. So now we're done. And again, the idea here would be I need to create maybe a short run production, but even if you look at this, where it's at, I could easily machine this most likely in 3-axis. If I wanted to, I could do 5, but it's probably not even needed. So again, the next thing other than 3D printing, maybe I put a little work in using freestyle, right? I create a cleaner version without all those lumps and bumps and things I don't like. Another option, again, here's where I might go into using Creo. Here's where I'm going to recreate it. But what I need to do because I recreated it, I probably want to do some analysis. So with this, really quickly, and notice when I do the analysis, the way I define the analysis is the same way I created the loads in generative, in live simulation, everything. And then we have some forces down here, right, on there, and this one here. That's going to be in the Y, 3,500. So with that, now we're good. We do our analysis. Very quickly, it's going to return the results and tell me that, where am I at here? 22, what load did I do? Let's look at our force over here again. Well, there we go. That didn't make sense. So now we do that. So here's where, again, the reason to go with Creo to do this, now I've got a 100% parametric model. If I take a look at it, I can say if I maybe change the height of the beam, I'm going to maybe reduce or eliminate that stress. So what do? Again, go back over to here. We look at the height, maybe make a quick change, and I use the graph. So now let's look at this. Take that and go to 27.5. And now we're going to regenerate. And again, the whole idea of using live simulation, I get immediate feedback. So now I got a part 156 megapascal. The material property is 240. I'm good to go. And again, I could take that, I could 3D print, I could do whatever. Last scenario, again, we've got the Kaizen bracket. Here's where I've got maybe an existing design, but I'm going to use this Kaizen approach to say, how can I make it better? The first thing I want to know is what's important. So here's my starting geometry, right? Here's my preserved geometry right through here. I've got that defined. What do we need to do? Same type of thing. We need to create our constraints and our load. So let's do that. Right? We've got our load over here. The force is on the bottom. There in the Y. 3,500. Now we take this. Here's where we're playing with the limit volume. Right? Now I'm going to say, hey, let's just back off the limit volume. So at 85%, show me what areas are most important. So very quickly, I'm going to take a model, look at it, do the analysis, and just by playing with the limit volume, I'm going to be able to see in my model what is most critical. So very quickly, it already started to get rid of these inner supports. And the more I back it off, right, there's the first iteration. If we go and do another quick change to it, let's maybe go to the 65. And within a very short amount of time, I'd be more than confident, not only what I saw before in CSL, I saw the stress in the main beam, but now using this, quite positive that the outer and these inner supports are not even needed. So then what would I do? I'd focus probably on recreating this part by focusing mainly on the main beam. So that quickly we took an existing part, using this whole idea of change for the better. I said, how do we make a better part? So just to show you that, and then we'll be wrapping it up. Let's go out of here. Let's close this one. And if we open up the final, there's our Kaizen bracket. And now we've got a part. Again, we've taken an existing part. We used it with generative to tell us what's important. We did a little bit of simulation. Now I got a part that is much less stress, well, kind of equal to the other, but now I greatly reduced the mass or the weight of that product. So hopefully pretty quick in 30 minutes, but hopefully I gave you some ideas about the workflows. So when you're using generative, again, what are you going to do with the output? It really depends. Do you want a prototype? Is it short run production? Is it high volume production? Or do you want to simply use it to look at an existing part and maybe figure out what you don't need, what's most critical to that design? So Rob, I'm a little bit over, but that's it.
That's quite all right that you're a little bit over. I thought this was really good. I thought it was excellent.
Good.
Yeah, because this unlike the other generative design webinars that we've done, it hasn't gone into the level of detail that you have. It was more of just a demo and what it can do, not necessarily digging into how to get to where you want to be.
Right.
Cool. So just to let everybody know, next week we have a webinar on project management for Windchill. So I'll be sending out a webinar invitation for that. And also, Jerry, you and I got to get together regarding a topic for the 29th.
I think behavioral modeling would be a good subject. A lot of use cases that a lot of people, if you're not familiar with it, you just don't think about where behavioral modeling would apply. So if that would work, I'd love to do that one.
Behavioral modeling, it will be.
Awesome.
Thanks, Jerry. So
you're welcome.
I'm going to have the recording posted up likely today on our YouTube page and send that link out to everybody so you can watch the recording. Feel free to share with your friends. So once again, everyone, thanks for being on today, for your time and your interest. And Jerry, thank you for your expertise. I really appreciate it.
Hey, you're welcome. Had fun.
Awesome. Thanks, everyone. Take care.
Bye all.